In the next podcasts, we are going to use analytical models to describe infiltration in soil. This is a nice illustration of the usefulness of analytical techniques such as introduced in the previous podcasts. We will look to infiltration, because infiltration is a very critical process in the soil hydrological cycle. In this course, we consider infiltration as a flux of water that will recharge the unsaturated soil at the soil-atmosphere interface. This infiltration flux determines the water that can be absorbed by the soil and hence becomes available for the different soil functions. It controls therefore the water status of the soil. If the incoming water flux is larger than the infiltration rate of the soil, a potential exists that water will be either stored at the soil surface or will flow along the surface as runoff. Infiltration therefore controls all the other fluxes of the hydrological cycle in terrestrial systems. In this and following podcasts, we will try to describe this process based on the soil physical principles that have been introduced previously. Let's start with the analysis of a simple experiment. Let's consider a homogeneous, isotropic, granular, flat soil that is initially dry. The system that you would like to model is the soil system, which has an infinite, semi-infinite thickness from the soil-atmosphere interface onwards. We look only to the vertical flow process in this soil. We therefore consider a vertical reference system with its origin at the soil surface. Let's subsequently consider that we add at a given time an amount of water on top of this soil, and let's suppose that this amount of water has an equivalent height of h surf. The amount of water that is added at the surface is therefore one of the boundary conditions of our system. Since this boundary condition is expressed in pressure head values or equivalent height, we call this a Dirichlet type boundary condition. Hence, at the soil surface we have a very small water pressure that corresponds to the vapor pressure, H air dry, and it becomes equal to the level of the water that we've added, H surf, when T increases. The question that we ask ourselves now is, how will the water profile evolve as a function of time in this soil? How will the suction head profile evolve? And how will the surface flux evolve? In order to analyze this, we look to a small video that shows what will occur in a real soil. In the video, see how the soil water infiltrates in a sandy soil. We see a clear infiltration front that wets up the soil, but we also see the position of the wetting front after 2, 3, 4 and 5 minutes of the experiment. At the right hand of the video we see the calculated water profiles using the soil hydrodynamic theory. In this case the profiles have been calculated with a numerical model. We will illustrate later on in this course some details of this numerical model. Now if we look in detail to the propagation of this infiltration front, we see that this propagation slows down with time. This is a key issue that we will explain shortly. Of course, since water content is related to suction head through the soil water retention curve, we can also look to the time course of the suction head profile as a function of time. Again, we observe that the apparent propagation velocity slows down. And how can we now explain the apparent slowing down of this infiltration velocity in this real soil? For understanding this, let's have a look to the energy of water that is available close to the infiltration surface. At the beginning of the experiment, the soil close to the soil surface is very dry. Hence, the soil will develop a large negative suction head. At the soil surface, we add an amount of water with an equivalent height h surf. This amount of water will create instantaneously a positive pressure at the soil surface. Hence, in the very small soil layer just below the interface, we will observe a large difference in the soil water potential at the interface and in the soil. The hydraulic gradient, which is the difference between this water potential divided by the distance, will be very large. Hence, following Darcy's law, and given the fact that the gradient drives the flow, we will have a very large water flux infiltrating in the soil. We should add a small remark. This initial conductivity of the soil is very low. But in Darcy's law, the hydraulic conductivity will be not so important, and the gradient will overrule the total flux. When infiltration now proceeds, the soil will wet up. Hence, the suction head close to the soil surface will decrease, and hence the hydraulic gradient will also decrease. The conductivity of the soil will also increase, but this increase is smaller than the decrease of the gradient. As a result, the Darcian flux will again decrease. As a result of all this, when we analyze infiltration on an initial dry soil, we will observe a decreasing infiltration rate as a function of time. This is the process that we want to model with our water flow theory. For doing this, we use the following symbols in the following sections. Jw is the Darcy flux. Hence, when we use a reference system for which the origin is located at the soil surface, then GWZ equals 0 and T corresponds to the actual infiltration flux. In the rest of the course, this is sometimes denoted with a small I. We refer to the intensity of the water flux at the soil surface, the infiltration intensity, or the actual infiltration. We also very often are interested in the cumulative amount of water that has been infiltrated. We use large I for this. This cumulative value, expressed in equivalent water heights, can be calculated by means of the time integral of the infiltration flux. So the shape of the instantaneous infiltration curve will be illustrated as here. While for the cumulative infiltration, we have rather a figure as illustrated here. In this figure, we make a difference between horizontal infiltration and vertical infiltration. Vertical infiltration for the same soil will be larger than horizontal infiltration. Indeed, for vertical infiltration, both the gravity and the capillarity potential contributes to infiltration. The gravity potential will increase the gradient and hence the infiltration flux in a given soil. A very interesting feature appears when plotting the cumulative infiltration in terms of the square root of time. When doing this, for the horizontal infiltration, we observe that the infiltration curve, which is in this case called the imbibition curve, aligns on a straight line. The slope of this curve is soil and experiment specific. We will come back to that very shortly. During the infiltration experiment, we can also analyze the wetting front. If the soil was initially homogeneously dry with a corresponding water content, theta I, then we know that all the soil water that has been infiltrated must be in the soil. With the mass conservation law, we can therefore express the cumulative infiltrated water in terms of the soil water content profile. The cumulative infiltration corresponds to the surface below the Z theta profile. In the hypothetical experiment where we add a large amount of water such that the water level appears at the soil surface instantaneously, we will immediately saturate the soil at the soil surface. Another situation occurs when we apply water at the flow rate, for instance by sprinkling water at the soil surface at a rate that is much more smaller than the potential infiltration rate. In this case, no ponding of water will occur, but water will still infiltrate. The soil water content at the soil surface, theta 0, will be smaller than saturated water content. In this case, the boundary condition of our flow problem will become a flux type boundary condition, often referred to as a Neumann boundary condition. Okay, with all this we can start analyze more in detail on our infiltration model. In most of the upcoming cases, we will use the Fokker-Planck model to describe infiltration. We should add a very small remark. Very often it is convenient to put a reference system with its origin at the soil surface that points downward. This means that the reference system points in the direction of the gravity field. In this case, we need of course to adapt the sign of the gravity term of the Fokker-Planck equation. In most of the cases that we will handle, this hypothesis will be made implicitly. With this, we are now ready to analyze the infiltration phenomena with mathematical models.